Well, hello everybody. This is the beginning of week 5, lecture number 1. I hope everybody's fine and not stressing out too much over these constant videos. I suppose the main thing is to try to keep up with everything. Yeah, do keep up. Don't leave trying to watch hundreds of hours of videos until the last minute of this term. So set yourself, just remember last year, if you were taking 6 courses, you would be in class for like 6 hours a day, and you should probably try to stick to sort of the same schedule this term. Just set aside a certain amount of time each day where you turn off your phone and your email and just sit down and watch videos and do the assignments and whatnot on a regular basis, and then you won't get behind, and then you won't be stressed out. You'll be happy. Okay, so today we're starting on chapter 4, which is common distributions, and we're going to start that with common discrete distributions. And basically, we start off with the very simplest of discrete random variables, the so-called Bernoulli trial. And really, this is the simplest. Basically, it's a trial. It has 2 possible outcomes. We can call it success, failure. We can map it to 0, 1. It can be any 2 possible outcomes: success, failure, 0, 1, black, white, yes, no, true, false, and so on and so forth. So you can't really think of a simpler random variable, and yet this particular random variable leads to 6 very common distributions that we're going to make use of this term, and also leads to another couple of families of distributions called Markov chains and queuing processes that we are not going to consider in this term. But if you're involved with traffic engineering or industrial engineers, will look at Markov processes in the next couple of years. Financial planning, weather modeling, all make use of Markov chains and queuing processes. Okay, so let's take a look at this particular random variable. First of all, if it's a random variable, so the most we can say about it is what is its distribution, its probability of taking on each of its possible values. Well, this is a sequence of trials, so we could have the second trial depend on the first trial, in which case the distribution is going to look something like this. What is the probability that x1 is 1 at the same time as x2 is 0? I shouldn't say at the same time if there's a sequence of trials, but the probability that x1 is 1 and x2 is 0 could be a conditional probability. The probability that x2 is 0 given that x1 is 1 times the probability that x1 equals 1. However, this could rapidly get very complicated, because if you've got 100 trials, then you've got possibly a probability distribution that involves probability that x1 is 1, x2 is something, x3 is something, and all the way up to 100, and that is very complicated possible distribution. So in general, we make some simplifying assumptions. As I said, we've got in general, we would have a distribution that looks something like this, and it's a product of very complicated conditional distributions. So we're going to make a simplifying assumption that trials are independent. That means then that the probability that x1 is 1 and x2 is 0, x3 is 0, and x4 is 0 is now just the product of the 4 probabilities. This is a whole lot easier, but we're going to make another simplifying assumption, and that the probabilities remain constant over time, so that the probability that x2 equals 0 is the same as the probability that x3 equals 0, and the probability that x1 equals 1 is the same as the probability that x4 equals 1. So now we just need to specify a single probability of success. We'll call that P. And so our distribution, and let's say success, I think we defined this up above here. So we let xi equals xi equals 1 if the ith trial is a success. I put success in quotes here because you can define success to be whatever it is one of these possible outcomes is, and sometimes I actually define success to be failure, because often it's system failure that we're really interested in. How many trials until the system fails, that sort of thing. Okay, so now we've got a single parameter P which is probability of one of these events, and we'll, just for simplicity, we'll call it success. And so the probability that xi is 1 is equal to p, and the probability that xi is 0 is 1 minus p, and we're going to call that q because we see this so often. We don't want to carry the 1 minus p around all the time. So now the probability that x1 is 1, x2 is 0, x3 is 0, and x4 is 1 is just the product of those four probabilities, which is going to be p for this one, times q for this one, times q for this one, times p for this one, which gives me p squared q squared. So the basic idea behind Bernoulli trials is that they have two possible outcomes, they are independent, and have constant probability of success. As I mentioned, Markov chains and queuing processes, all we're having to do there is generalize the Bernoulli trial a little bit to more than two possible outcomes, and we allow some dependence between trials. But like I said, we're not going to consider that, but these are another set of very powerful processes, random processes, that are very commonly used, and they all derive from this basic idea of a Bernoulli trial. Well, what are the main characteristics of this simple random variable? We could talk about the expected value, or the mean of this expected value of xi is the sum of its possible values times their probability of occurrence. So one possible value is 0, and its probability of occurrence is probability that x equals 0, and the other possible value is 1 times the probability of that occurring, and we get 0 times q plus 1 times p. Of course, the first term disappears, and we just get p. So the expected value of xi is just the probability of success. Variance of xi, our fundamental expression, is the variance is the expected value of xi squared minus the expectation squared of xi. And so we know what the expected value of xi is, that's just p, so I'm just going to subtract p squared here. And the expected value of xi squared is the possible values of xi squared times their probability of occurrence. So 0 squared times q plus 1 squared times p minus the expectation squared, which is p squared. This first term disappears again. 1 squared, of course, is 1, so I get p minus p squared. And I can factor the p out. I get p times 1 minus p, and 1 minus p is just q. So the variance of xi is just p times q. Okay, so this very simple random variable leads to 6 common distributions. And then I've divided these up into 2 groups. The left-hand side I call the binomial family, and they're composed of 3 distributions, and these just answer different questions about a sequence of trials. The first one is binomial, and we're going to call that n sub n, and as we'll see shortly, that's the number of successes in n trials. The next one is geometric, and we're going to call that T1, and that is the number of trials until the first success. And the final one in this family is negative binomial, which is we'll call that T sub k, and that's the number of trials till the kth success. Then we get another set of 3 distributions, which I call the Poisson family, and this set arises if we decide to let every single instant in time become a trial. So now we've got an infinite number of trials. Successes can occur at any instant in time. So these are more commonly used for arrival processes. Person arrives at a bank or your website. A hurricane strikes Halifax, and so on and so forth. So these occur. They can occur at any instant in time. So we have every instant becomes a trial, and we get 3 more distributions. The one is called Poisson, and we're going to call it n sub t. And this is a number of successes or arrival in time interval t. Exponential is the analogy to geometric, and I'm still calling it T1. This is the time now to the first arrival or first success. It can actually be the time to the next arrival or next success, because again, we're still talking about a sequence of independent trials, so it doesn't matter when you start looking. This one here will be the time until the next success or next arrival. And then the gamma is the analogy to negative binomial. We'll also call that T sub k, and this is the time now to the third success or third arrival. Anyhow, we'll look at all these 6 distributions in more detail in this lecture. Okay, first of all, binomial distribution. Basically, we're going to define nn to be the number of successes in n trials. The basic idea here is that we have a sequence of trials, Let's just write this. So we got a sequence of trials, and I'll write these as dashes. And in each trial, we get either a success or a failure. Okay, so we could have a success here, failure here, success, failure, and so on and so forth. Dot, dot, dot. So what the binomial distribution is modeling is it's counting the number of successes that occur in n trials. We know that if each of these things is mapped to a number, then the successes we're going to say are ones, the failures we're going to be zeros, and so that basically the number of successes can be obtained just by adding up these numbers of random variables xi. Okay, so that if xi is a 1, then it counts as success. If it's a 0, it's counting a failure. So if I add up all these xi's, I'm just going to get the number of successes in the n trials. So in other words, n sub n can be expressed as a sum I equals 1 to n of xi. So there's a mathematical expression here now. So basically, we know n sub n is a random variable. This particular realization here gave me 1, 2 successes in 5 trials. But the next time I run this test, I might get 3 successes in 5 trials, and the time after that, I might get no successes in 5 trials. So this is a random variable. And so we have to define its distribution. So to do that, we have to come up with a set of numbers, probably that n sub n is equal to m. And our possible values of m are 0, we could have no successes, 1, we could have 1 success, and so on and so forth up to n. We cannot have more than n successes in n trials. So m goes from 0 to m. 0 to n. Well, how do we get this distribution? Let's start by considering a specific case, probably that n4 is equal to 2. And this would mean that we've had 2 successes in, well, that should be 4 trials. Let me just correct that. 4 trials. In other words, we could have had SSFF, or we could have SFSF, or SFFS, or dot, dot, dot. Okay, any of these sequences lead to 2 successes in 4 trials. Okay. In other words, we can write probably that n4 is equal to 2 is the probability that we got a success in the first trial. That's what we're seeing over here. That x1 is 1, and that x2 is 1. That's what we're seeing here. And that x3 is 0, and that x4 is 0. That's what we're seeing here. This is 0, 0. Maybe I'll just change these into 1s. This is a 1, 1. Oops. Oh. 1, 1. Okay. The next one, we have a 1, a 0, a 1, and a 0. And this one we had a 1, a 0, 0, 1. So basically the expressions of these come down here below. This is the second set, there where we got a success on the first one, and then a failure, then a success, and then a failure. And the third one we had a success, 2 failures, and a success, and so on and so forth. Well, this is a union of a sequence of numbers. So these ORs here come in, they turn into unions. So the question is this event here disjoint from this event here? Well, clearly, if we had SSFF, we cannot have had SFSF, so that these 2 things are disjoint. In fact, all of these particular sequences are disjoint from one another. If I had this one, I cannot have had this one, and so on and so forth. So the answer to that question is yes, and that means that these unions turn into plus signs. Okay, so we just add up these probabilities. We've already decided that these events are independent, so that this probability of these 4 events happening, x1 is 1, and x2 is 1, and x3 is 0, and x4 is equal to 0, is just probability that x1 equals 1 times the probability that x2 equals 1, times the probability that x3 equals 0, times the probability that x4 equals 0, and that's just p times q, which is p squared q squared. We already saw that in an earlier example, above, I guess. And then same thing here. I've got p Q, P, Q. So that's also P squared, Q squared. And here as well, P, Q, Q, P squared, Q squared. So that basically I'm getting the sum of a bunch of P squared times Q squareds. And the main thing I have to do is find out how many of these terms I have. Well, it turns out that what I'm doing here is I've got 4 trials, and I'm selecting 2 of them to put the S's in. And I don't care about the order in which I select those 2 trials. So that the total number of ways of doing that is just going to be 4 choose 2. 4 trials, choosing 2 of them to put the S's in, and without regard to order, it gives me the number of ways of sticking 2 S's into the 4 trials. So that probability that I'm looking for here, n4 equals 2, is just 4 choose 2 times P squared times Q squared. And in general then, probability that I have m successes in n trials is n choose m, so I'm choosing from my n trials m successes, times I've had m successes, so p is raised to the power m, and the rest are failures, so q is raised to the power n minus m. And this then is the distribution that I get for the binomial. Well, then we could talk about the main characteristics of the binomial distribution, starting with its mean. The fundamental definition of a mean or expectation is the sum of all possible values times the probability of occurrence. So I could write it this way: expected value of n sub n is the sum m equals 0 to n, those are the possible values of this random variable, times their probability of occurrence. And I got this horrible looking expression on the right hand side, m times n choose m, p to the m, q to the m minus 1. And this is not an easy expression to solve. Basically, if I were to solve it, I just look up what the answer is because somebody else has solved it for me. The much simpler way of approaching this problem is to recall that n sub n is the sum of these Bernoulli trials. I equals 1 to n of xi's, and where these are 1s, we get a success, and so I'm just counting up the number of 1s, which is the number of successes. That means the expected value of this is just the expected value of this sum. And recall, expectation of a sum is sum of expectations, so I can bring the e inside here, and I get this sum I equals 1 of the expected, 1 to n of the expected value of xi, and each of these we saw earlier was just p. So all I'm getting is p plus p n times, which gives me n times p. And intuitively this makes sense. We know that 20% of the time we have a success, then if I have 100 trials, I expect to see 20 successes. So 0.2 times 100 gives me my 20 successes. Similarly, to get the variance, we talk about the easier way of doing this, rather than looking at the sum of all possible values of m squared times this thing, is just to look at the fact that n sub n is this sum. So I end up with the variance of a sum. And if you recall, the variance of a sum is the sum of all possible covariances, unless these things are independent. If they're independent, then the variance of a sum becomes the sum of the variances, which is much simpler. So basically, variance of n sub n becomes the sum I equals 1 to n of the variance of xi, and we saw that each of those was p times q. So I got p times q plus p times q n times, and that means that the variance of n sub n is just n pq. And you should remember this one because we're going to see this again later when we're talking about statistics. It comes into play when we have variances of averages, for example. Okay, let's look at an example. Let's assume we have a Bernoulli sequence consisting of 3 trials and let n3 equals x1 plus x2 plus x3. So we've got n3 then is the number of successes in 3 trials. And then the question is, what is the probability that n3 equals I for the possible values of I? Well, if we have 3 trials, we could have 0 successes, we could have 1, 2, or 3 successes. We can't have more than 3. So we got 4 numbers to evaluate here. Okay. So we start with probability that n3 is equal to 0. We've had 0 successes, so the power on p must be 0. And that means we've had 3 failures, so the power on q must be 3. And we're choosing 0 results from 3, so there's only one way of having this happen. If n3 is 0, then we have to have had 3 failures. Okay, so the end result of this is q cubed. Then we look at probability that n3 equals 1. So now I've got 1 success, so the power on p is 1. And that means I've had 2 failures, so the power on q is 2. And there are 3 ways of having that 1 success in the 3 trials. So 3 choose 1. So I got 3 times p q squared. Probability that n3 equals 2 turns out to be the same, because now it's just the number of ways of putting 1 failure in my 3 trials. So that number of ways of doing that is 3 choose 2 for the 2 successes, or 3 choose 1 if we talk about the failure. But we've now had 2 successes, so the power on p is 2, and 1 failure, so the power on q is 1. So I got, oh, what am I talking about? Yeah, okay, I made a mistake. The number of ways of doing it is the same, but the powers change. Okay, so this is not exactly the same as this one up here. The number of ways is the same, but it's now p squared times q. And then the number of ways of doing 3 successes in 3 trials. All of them have to be successes, so 3 choose 3. Here gives me 1 way of doing that. The power on p must now be 3, and the power on q must be 0, so I get p cubed. And these numbers should all add up to 1. Okay, another example, 4.2. Let's suppose that a system contains 10 independent components with individual failure probability of 0.2. So the key word here is independent, and that they all have the same probability of failure. This means that really this system is made up of a series of trials, 10 trials to be precise, and each of those trials are independent and they have constant probability of success. So these are Bernoulli trials. So this sort of thought process is what you're going to have to do when you go through these worded problems. You have to look at it and say, okay, is this a sequence of trials? If so, how many are there? Are they independent? And do they have constant probability of success? If the answer to those things are all yes, then this is a sequence of Bernoulli trials. So the question here is, given that 1 component has failed, what is the probability that at least 2 components have failed? Well, that's sort of a weird question, because if you interpret that to mean, given that exactly 1 component has failed, what is the probability that at least 2 components have failed, then that probability must be 0. But I think I'm going to interpret this as meaning, given that I know 1 component has failed, what is the probability that more have failed? So that's how I'm going to interpret that question. So we start by defining our random variable. So we're going to let n sub 10, so that's for the 10 trials that we have here, be the number of components that fail. Now here's a situation where I'm calling success, in quotes, failure. Because the thing of interest in this question is the probability of failure. So I'm going to let that be the x equals 1 situation. So n10 is the number of components that fail out of the 10. And since components fail independently with constant probability, and there are only 2 possible outcomes, failure versus survival, then n10 follows a binomial distribution with p equals 0.2. So what we're looking for is the probability that n10 is greater than or equal to 2, given that n10 is greater than or equal to 1. So this goes back to this statement here. Given that 1 component has failed, I'm interpreting that as meaning that at least 1 component. I know 1, but it's really that at least 1 component has failed. And that's the given information here. Okay, so we know that a conditional, there's a number of ways we could write this. We can use Bayes' theorem to flip the conditional around, but that doesn't really help us because we don't know probably that n10 is greater than or equal to 1, given that n10 is greater than or equal to 2, so Bayes' theorem won't help us. It's better to go to the intermediate step where this conditional probability is the probability of the intersection divided by the probability of the given part. Okay, so it's probability of n10 greater than or equal to 2, intersection n10 greater than or equal to 1, divided by the probability that n10 is greater than or equal to 1. Well, if you look closely at the top, this intersection must just be this part of it, because this n10 because n10 greater than or equal to 2 is a subset of n10 greater than or equal to 1. All of the elements in this are also in this. So their intersection is just going to be the first part. So I end up with n10 greater or equal to 2 divided by the probability of n10 greater or equal to 1. And those things I can now evaluate from the binomial distribution. probability that n10 is greater or equal to 1, I can add up probability that n10 equals 1 plus probability that n10 equals 2 all the way up to 10. Or a much simpler way is just to take that as 1 minus the probability that n10 is less than 1, which is probability that n10 equals 0. So 1 minus probability that n10 equals 0 is 1 minus 10 choose 0. I've now had 0 successes, or in this case failures, and their probability is 0.2, so the power on that is 0. And I've had 10 successes, for survivals in this case, and so the power on that is 10. And I get 0.8926. That's the thing on the bottom. So now I need to compute the thing on the top. Again, I'm going to take probability that n10 is greater or equal to 2 is this part here. We already know that's 0.8926. And I subtract another part, which is probably that n10 equals 1. And plug in all the numbers, I get 0.6242. And now I can compute this probability that n10 is greater or equal to 2, given n10 is greater than or equal to 1, is 0.6242 divided by 0.8926, which gives me about 0.7. And that concludes the first lecture of this week. Went very quickly. The main task now is to go through lots of examples, questions. Your assignments will have some. I posted other questions on the web page. And get used to how to interpret worded questions in terms of these distributions. So I think the important thing to remember is that n sub n is the number of successes in n trials. And so when you're looking at a question, that's what you're looking to see if that's what the question is asking for. We'll look at next lecture at geometric and negative binomial. Geometric is the number of trials until the first success, and that basically is a different question about this sequence of trials. So you have to look at the worded English worded questions that you're faced with, and decide which of these three distributions it's going to be asking about. Well, first of all, you have to decide, is it actually a sequence of Bernoulli trials in the first place? And there you say, okay, yeah, are there two possible outcomes? Are they independent? And do they have constant probability of success or failure? Okay, that's it for today. Thank you.